Hello dear students, welcome to the lecture on water potential and its components. In today's deliberations, we shall learn the concept of chemical potential and water potential. We shall understand the major components of water potential, that is osmotic potential and pressure potential. We shall also comprehend other components of water potential, that is gravity potential and matric potential. We shall also know underlying principle of osmosis. Besides, we shall study the various factors affecting water potential. Finally, we will appreciate the significance of water potential in plant-water relations. First, let me give a brief introduction about various transport processes and their associated driving forces. We know that movement or transport of substances from one region to another is called translocation. Translocation may occur either by active or passive processes, depending on whether metabolic energy is used or not. There is no evidence for the direct expenditure of energy during water transport. Therefore, the translocation of water is considered a passive process. Passive movement of most substances can occur by one of two physical processes, either diffusion or bulk flow. Now, what is diffusion? Diffusion is regarded as a directed movement from a region of high concentration to a region of lower concentration, accomplished through the random thermal motion of individual molecules. Thus, diffusion occurs down a concentration gradient. In other words, the driving force for diffusion is concentration gradient or concentration difference. Bulk flow or mass flow is the concerted movement of groups of molecules en masse, most often in response to a pressure gradient. For example, a river flowing, water running through the pipes. Bulk flow occurs down a pressure gradient. That is, the driving force for bulk flow is pressure gradient or pressure difference. Let us now take osmosis. What is osmosis? It is actually a special type of diffusion through a selectively permeable membrane. Simply, osmosis is the movement of water from a region of higher water concentration to a region of lower water concentration through a selectively permeable membrane. While the concentration and pressure gradients are the driving forces for diffusion and bulk flow respectively, osmosis occurs spontaneously in response to a total driving force of both these gradients. That is, the direction and rate of water flow across a membrane are determined not only by the concentration gradient of water or by the pressure gradient, but by the sum of these two driving forces. In other words, the driving force for the osmosis is the sum of the driving force of concentration gradient and pressure gradient. This total driving force represents the free energy gradient of water. Consider two chambers A and B, A containing solution and B containing pure water, both separated by a selectively permeable membrane. Initially, water level in both the chambers is same. However, after some time, water level in chamber A increases while that in chamber B decreases. This increase in water level of chamber A is due to the movement of water molecules from chamber B to chamber A through the selectively permeable membrane, that is from pure water to solution. This movement of water from a region of higher water concentration, pure water, to a region of lower water concentration, solution, through a selectively permeable membrane is called osmosis. The movement of water from chamber B to A will continue until equilibrium is attained. when the driving force reaches 0. This total driving force, that is sum of concentration gradient and pressure gradient, represents the free energy gradient of water. The free energy of pure water, that is chamber B, is greater than the free energy of water in the solution, that is chamber A. Therefore, water will move in response to free energy gradient from chamber B to A till equilibrium is reached. It is not the free energy per se, but the free energy of water per unit volume called water potential. That is actually the driving force for osmosis. In other words, water potential of pure water, that is chamber B, is greater than the water potential of water in the solution, that is chamber A. Therefore, water will move in response to water potential gradient from chamber B to A till equilibrium is reached, when the water potential in both the chambers would be same. Now let us study the concept of chemical potential and water potential. The energy content of water, like any other substance, is easily determined in terms of its chemical potential. But what is chemical potential? Chemical potential is defined as the free energy per mole of the substance, and free energy represents the potential to perform work. Thus, chemical potential is a measure of the capacity of a substance to react or move. Its units are joules per mole. Plant physiologists have most often used a related parameter called water potential to represent the potential of water to perform work or to react or move. However, water potential is not synonymous with the chemical potential of water. Water potential is defined as the chemical potential of water divided by the partial molar volume of water. Mathematically, we write it as psi W is equal to mu W divided by V W, where psi W represents the water potential, mu W represents the chemical potential of water, and V W represents the partial molar volume of water. Since chemical potential is the free energy per mole of the substance, we can write it mathematically like this: mu W is equal to G divided by N, where G indicates free energy and N the number of moles, while partial molar volume of water is the volume per mole of the substance. Here mathematically we can write it like this: VW is equal to V divided by N, where VW is the partial molar volume of water, V is the volume, and N the moles of water. Putting the value of mu W, that is chemical potential, and VW, that is partial molar volume, in equation above, we get water potential is equal to G divided by N whole divided by V divided by N, and that is finally equal to G by V, because N and N will cancel. Now, thus water potential is a measure of the free energy of water per unit volume, the units being joules per meter cube. These units are equivalent to pressure units such as the Pascal, which is the common measurement unit for water potential. The difference in chemical potential of a substance between two regions is the driving force for its spontaneous transfer from one region to another. Thus, in case of water, it is the difference of water potential between two regions that is the driving force for its spontaneous transfer from one region to another. In other words, the transport of water occurs along a water potential gradient, that is from higher to lower water potential. Absolute values of chemical potential of most substances cannot be easily measured. Therefore, relative values in terms of difference in chemical potential between two states are measured, where one of the state is usually taken as a reference state. Same is the case with water potential, as relative values rather than absolute values are taken. In case of water, the reference state is pure liquid water at atmospheric pressure and the same temperature as the system under investigation. Water potential in the reference state, that is pure water, is arbitrarily assigned a value of 0 megapascals. Now, let us study the various factors affecting water potential. The water potential that produces the driving force for the movement of water depends on following factors. Number 1, concentration or activity of water. Just like chemical potential is directly proportional to the concentration or activity of a substance, water potential is also directly proportional to its concentration or activity. However, water potential is inversely proportional to solute concentration. In solutions, solute particles decrease the chemical potential of solvent molecules and hence the water potential. This is due to the fact that the mole fraction of the solvent gets decreased. Mole fraction of solvent, as you know, is equal to moles of solvent divided by total moles of the solution. That is, mole fraction of solvent is equal to moles of solvent divided by moles of solvent plus moles of solute. Therefore, water potential or chemical potential of water depends on the mole fraction of water, which takes into account both the solvent and the solute concentration. Chemical potential of water is related to mole fraction of water by the following equation. Mu W is equal to mu W naught plus RT natural log of XW, where mu W is the chemical potential of water under ambient conditions, mu W naught is the chemical potential under standard conditions, R is gas constant, T is temperature, and XW indicates the mole fraction of water. Another factor is pressure. Increasing the pressure increases the free energy and hence the chemical potential or water potential. Chemical potential of water is related to pressure by the equation mu W is equal to VW into P, where mu W is the chemical potential of water, VW is the partial molar volume of water, and P is the pressure, that is hydrostatic pressure. The next factor is temperature. Chemical potential or water potential also increases with increase in temperature because of the thermal agitation of molecules. But the effect of temperature is usually ignored because the temperature is assumed to be constant in a system. One more factor, that is matrix. A material with surfaces that bind water is called a matrix. Many charged molecules or surfaces, for example clay particles, proteins, cell wall polysaccharides, form electrostatic interactions with polar water molecules and therefore bind water. Binding is a spontaneous process that releases free energy, thereby decreasing chemical potential or water potential. However, when the matrix is saturated with water, the contribution of matrix to water potential is 0. Adding above equations of pressure and solute concentrations, for example equation 5 and 6, and taking some assumptions and mathematical calculations, we finally get mu W minus mu W naught is equal to VW into P minus pi, where mu W is the chemical potential of water, mu W naught is the chemical potential of water under standard conditions, P is hydrostatic pressure and pi is osmotic pressure. As per this equation, the chemical potential of water in a solution differs from that of pure water under standard conditions as a function of osmotic component and a pressure component. Rearranging the above equation and taking mu W naught, that is chemical potential under standard condition, is equal to 0, we get psi W is equal to mu W divided by V W, that is water potential is equal to the chemical potential of water divided by partial molar volume of water, and that is equal to P minus pi, that is hydrostatic pressure minus osmotic pressure, and that is equal to minus dPd, that is minus diffusion pressure deficit, because you know that dPd is equal to pi minus P, that is osmotic pressure minus hydrostatic pressure. Thus, water potential can also be defined as the difference between hydrostatic pressure and osmotic pressure, or as a negative of diffusion pressure deficit. Water potential is also expressed as the algebraic sum of pressure potential and osmotic potential. Mathematically, we can write it like this: psi W is equal to psi P plus psi S, where psi W indicates the water potential, psi W indicates the pressure potential, and psi S indicates the solute potential. Water potential is also expressed as psi W is equal to GW minus GW naught divided by V, where GW indicates the free energy of water under ambient conditions, GW naught indicates the free energy of water under standard conditions, and V indicates the volume, and that is actually equal to change in free energy of water divided by volume, delta GW divided by V. So, as per this equation, water potential is also defined thermodynamically as the amount of work that becomes available when a mole of water in the system is transferred isothermally and reversibly from pure water to a point in the system. This work is equivalent to the difference in free energy per unit volume of water in the system and pure water at the same temperature. Now, let us discuss the components of water potential. The major factors influencing the water potential in plants are concentration and hydrostatic pressure. Thus, total water potential can be partitioned into two major component potentials, that is osmotic potential and pressure potential, as given in the following equation. Psi W is equal to psi P plus psi S, where psi W indicates the water potential, psi P indicates the pressure potential, psi S indicates the osmotic potential. The two components of water potential can be easily demonstrated by using a device called osmometer. It is constructed by closing off the open end of a thistle tube with a selectively permeable membrane. The tube is then filled with a sugar solution and inverted in a container of pure water. Now, let us take the different components of water potential. First, the osmotic potential. In an osmometer, the volume of solution in the tube will increase over time due to a net diffusion of water across a membrane from pure water into a solution. It is because pure water has more water potential, free energy per unit volume, than that in the solution. The increase in the volume of the solution will continue until the hydrostatic pressure developed in the tube is sufficient enough to balance the force driving the water into the solution. Alternatively, the tube could be fitted with a piston to measure the amount of force required to just prevent any increase in the volume of solution. This force, measured in units of pressure, that is force per unit area, is known as osmotic pressure, indicated by pi. The magnitude of osmotic pressure is a function of solute concentration. An isolated solution cannot have an osmotic pressure, but has only the potential to manifest a pressure when placed in an osmometer. Therefore, we say that the solution has an osmotic potential, which is shown by psi s, that is solute potential. Since osmotic potential and osmotic pressure are equal but opposite forces, osmotic potential is regarded as the negative of the osmotic pressure, that is psi s is equal to minus pi, that is solute potential or osmotic potential is equal to negative of osmotic pressure. The term osmotic potential or solute potential is preferred over osmotic pressure because it is more properly a property of the solution. Osmotic potential is also called solute potential, hence designated as psi s, because it represents the effect of dissolved solutes on water potential. Solutes reduce the free energy of water by diluting the water. Osmotic potential depends on the total number of solute particles in the solution but is independent of the specific nature of the solute. J.H. Van't Hoff in 1887 discovered an empirical relationship between osmotic potential and molar concentration of a solution called Van't Hoff equation, which is given below. Solute potential is equal to minus MIRT, where R is gas constant, T is absolute temperature in degrees Kelvin, I is constant called Van't Hoff's factor that accounts for ionization of the solute and other deviations from perfect solutions. For non-ionized molecules, I is equal to 1, and M is the solute concentration of the solution expressed as osmolarity, moles of total dissolved solutes per liter of water. The minus sign indicates that dissolved solutes reduce the water potential of a solution relative to the reference state of pure water. Thus, solute potential is the amount by which water potential is reduced as a result of the presence of solute. The next component, that is pressure potential. When a cell, which also serves as an osmotic system, is placed in pure water, there occurs endosmosis, just like that in the laboratory osmometer. It results in the build-up pressure called hydrostatic pressure within the system, manifested either as a raising of liquid in tube of osmometer or a pressure upon the cell wall in case of cell. Increasing pressure will raise the water potential, and so the water potential within the osmotic system will begin to increase toward zero, that is equal to the water potential of pure water on the other side. At this point, water potential gradient will be 0 and equilibrium is reached. Thus, equilibrium is reached due to the increase in hydrostatic pressure. The hydrostatic pressure is also called pressure potential. Therefore, the relationship between water potential and its components may be expressed either as psi w is equal to P minus pi, where psi w indicates water potential, P hydrostatic pressure and pi osmotic pressure. Or it can be also written as psi w is equal to psi p plus psi s, where psi w indicates water potential, psi p indicates pressure potential and psi s indicates osmotic potential. The hydrostatic pressure is measured as the deviation from the ambient atmospheric pressure, that is, the difference between actual pressure and atmospheric pressure. By convention, this P is equal to 0 at atmospheric pressure, that is, when P in a cell or osmometer is equal to atmospheric pressure. So, under such circumstances, psi P is equal to 0. Hydrostatic pressure can have any value, positive, 0 or negative. Positive pressure raises the water potential while negative pressures reduce it. The positive hydrostatic pressure within cell is called turgor pressure. The turgor pressure is directed outward, exerted by the expanding protoplast on the cell wall. It is equal in magnitude but opposite in direction to the inward pressure called wall pressure, which is exerted by the cell wall. A cell experiencing turgor pressure is said to be turgid. A cell that experiences water loss to the point where turgor pressure is reduced to 0 is said to be flaccid. Living plant cells are typically assumed to have only positive pressures. However, negative hydrostatic pressure called tension can also occur in some cells such as dead xylem elements and in the walls between cells. Osmotic potential and pressure potential are the two major components of the water potential. Besides osmotic potential and pressure potential, there are two more components, the gravity potential and matric potential, which contribute to the total water potential, although to a lesser extent. Thus, we can write water potential is equal to pressure potential plus solute potential plus gravity potential plus matric potential. Now, what is this gravity potential? Gravity causes water to move downward unless the force of gravity is opposed by an equal and opposite force. That component of water potential which is contributed by force of gravity is called gravity potential. It is denoted by psi g. The term gravity potential depends on the height of the water above the reference state water, the density of water, and the acceleration due to gravity. Mathematically, it can be written like this: psi g is equal to rho w into g into h, where psi w indicates gravity potential, rho w indicates the density of water, g the force of gravity, and h is the height. Now, putting the values of rho w and g, we can get a value of 0.01 megapascals per meter. That means a vertical distance of 10 meters translates into a 0.1 megapascal change in water potential. At cellular level, the gravitational component is generally ignored because it is negligible as compared to the osmotic potential and the pressure potential. Thus, in these cases, the aforementioned equation can be again simplified as follows: psi w is equal to pressure potential plus solute potential plus matric potential, because the gravity potential is negligible. Now, the next component is matric potential. Hydrophilic surfaces and many charged surfaces, for example, clay particles, proteins, cell wall polysaccharides, form electrostatic interactions with polar water molecules and bind or adsorb water. Such a material with surfaces that adsorb water is called a matrix. Even surfaces with no net charge, for example starch, can also bind water because of hydrogen binding. Binding is a spontaneous process that releases free energy, that is, delta G is negative, thereby decreasing chemical potential or water potential. Thus, matrix also affects the water potential, and that component of water potential which is contributed by matrix is called matric potential. The absorption of water by hydrophilic surfaces, that is matrix, is called hydration or imbibition. The tenacity with which the water molecules are adsorbed depends not only on the nature of the surfaces but also on the distance between the surface and the adsorbed water molecules. Nearer the water molecules, higher the tenacity. The average tenacity with which the least tightly held most distant layer of water molecules is adsorbed gives the tendency of a matrix to adsorb additional water molecules. This tendency of a matrix to adsorb additional water molecules is called matric potential. Matric potential has same units as water potential. Matric potential, like osmotic potential, is always negative except when matrix is saturated with excess of pure water. A dry matrix such as filter paper, wood, soil, gelatin often has an extremely negative matric potential. It can be as low as -300 megapascals, while the same matrix in a large volume of pure water at atmospheric pressure has matric potential of 0. Because being saturated, it is in equilibrium with surrounding water and does not have tendency to adsorb additional water molecules. In a complex system such as a cell, the final water potential will be determined not only by osmotic and pressure components but also by the matric effects of the proteins and other surfaces. Hence, matric potential can play an important role in plants, especially during hydration of membranes, proteins, ribosomes, and several components of cell wall. It is particularly important in the early stages of water uptake by dry seeds, called imbibition, and hydration of cell walls, wood and soil. However, in cytosol, the contribution of the matric component to final water potential is very small and negligible as compared with osmotic component of ions and molecules at equivalent weights. It is also difficult to distinguish the matric component from osmotic potential. Consequently, matric potential is not considered as a component of the water potential in the same sense as that of osmotic pressure and pressure potentials. Therefore, it is generally not valid to add matric potential to solute potential and pressure potential to arrive at total water potential. Thus, the equation again becomes water potential is equal to pressure potential plus solute potential. Finally, let us appreciate the significance of water potential in plant-water relations. The significance of water potential in plant-water relations is below. Number 1, water potential governs the transport of water across cell membranes and from one part of the plant to other. It especially governs the transport of water from the soil through the plant to the atmosphere, that is through SPAC, soil plant atmospheric continuum. Water potential not only determines the direction of transport but also the magnitude of the driving force. Water potential determines the rate of water movement, that is flux, by Fick's law as follows. Tau is equal to psi W1 minus psi W2 whole divided by R, where tau is the water flux density, that is given as grams per meter square per second, or flow rate, that is meter cube per meter square per second, where psi W1 and psi W2 is the water potential at highest and lowest point respectively, and R is the resistance to flow. Water potential is also a useful measure of the water status of the plants. It helps to find how hydrated a plant is and thus provides a relative index of the water stress the plant is experiencing. For example, water potential of well-watered plants is -0.2 to -1 megapascals. Water potential of mild water stress can range from -1 to -2 megapascals. And water potential of arid desert climate can be lower than -2 megapascals. That is, it can range from -2 to -5 megapascals. Now that is all about water potential and its components. Thank you.